Hello everyone and welcome back. Till the previous session, we have seen all the different arithmetic group of instructions, and specifically in the last session, we summarized all of them. It's time to concretize all those concepts. So welcome to the session, Arithmetic Instructions Solve Problems. Without any further ado, let's get to learning. Coming to the topic that we are going to cover in this session, today we will solve some problems on arithmetic instructions. Consider the question. Assume that before execution of any instruction, we have A equals 65H. This means the accumulator or the A register is to be loaded with the value 65H. The general purpose register B is to be loaded with the value B2H. Then the general purpose register H is to be loaded with the value F9H. The GPRL is to be loaded with 50H. And the carry flag is to be set to 1. And at the same time, the content of the memory location, which is mentioned in here, F950, it will contain 38H value before the execution of any instruction. So which instructions we are talking about? These 5 instructions. Now we are supposed to find out what is the value of the A register or the accumulator register and the value of the different flags within the flags register after the execution of these following instructions. So we are going to have a single question, but it has got 5 different parts. And remember, before we execute any of these instructions, the contents which already have been mentioned will remain the same. Let me highlight the contents for you. Now let's fill these values in the programmer's view of 8085 microprocessor. So in the A register, we are supposed to load the value 65H. So let's do that. In B, we are supposed to load B2H. So we will load that into the B register. The H register has the value F9H. The L register is supposed to have the value 50H. Now if you notice, the HL register pair is containing the location F950 of the memory, to which we are supposed to load the value 38H. So we already loaded that. So let's now focus on the first instruction, that is ADDL. Now we already know what this instruction will do. It will add the content of the L register, which is currently having the value 50, with the accumulator's content, which is 65. So we are going to perform the addition of 65H with 50H. Let's begin. 5 plus 0 will give us the result 5. What about 6 plus 5? 11 in decimal, but in hexadecimal it is B. Now we are supposed to find out the value of the A register. So after the operation, the value, that is B5, is to be loaded in the accumulator register. Now the 4-bit binary of 5 is 0101. What about B? B is 11 and in binary it is 1011. So within the accumulator, the outcome, that is B5, will be loaded. So that's the value inside the A register after the addition has been performed. Let's now check the flags register. Now if you remember, initially the carry flag was set, right? But now look at the operation. After the addition was done, it didn't generate any carry. So the carry will be reset to 0. What about P flag or parity flag? It is to be set to 1 if the contents within the accumulator has even number of 1s. Do we have that in here? Let's count. 1, 2, 3, 4, 5. 5 is an odd number, right? So the parity flag is going to be reset to 0. What about auxiliary carry flag? If you notice the least significant digits, 5 and 0. Addition of these two resulted in the sum 5. So no carry, right? So the auxiliary carry will also be reset to 0. Let's talk about the Z flag now. The Z flag is supposed to be set if within the accumulator we have got all zeros. Is that the case here? No, right? So the Z flag will be reset. Now what about the S flag or sign flag? The sign flag is set if in the accumulator the most significant bit is 1. Here it is 1 as well. Therefore, in the flags register, the sign flag will be set to 1. So clearly, if we have within the accumulator 65H, and if in the L register we have got 50H, after the execution of the instruction ADDL, within the accumulator we will have the value B5, and in the flags register, only the sign flag will be set. So we are done with the execution of the first instruction. Let's now focus on the second instruction, that is ADCB. Now I hope you remember what ADC does. Add with carry the content of B register with the content of the accumulator. Now in B register we have got B2 as it was mentioned in the question itself, and in the accumulator we have got 65. So we are performing addition between 65 and B2, and if you remember, the carry flag was initially set. So we are going to perform the addition between 65, B2 and 1 of carry. Now if we add this 1 with B2, it will become B3. Now let's perform the addition. Adding 5 with 3, we will obtain the result 8. Now 6 added with B, that is 11 of decimal, we will have the result as 17. Now think about it. In case of hexadecimal, 15 is F. So 16 is going to be 10 and 17 will be 11. So we will get the result as 11. Now notice, it's a 3-digit hexadecimal number. But within the accumulator, we can only store 2 digits. Now the 4-bit binary of 8 is 1000 and the 4-bit binary of 1 is 0001. What about the carry? Well, it will set the carry flag to 1. So after the addition, within the accumulator register, the value 18 will be updated. So this is the content of the A register after the execution of ADCB. Let's now check out the contents of the flags register. What about the parity flag? In order to set this to 1, within the accumulator, we should have even number of 1s. Observe, here we have got 2 1s in the content of the accumulator. So yes, 2 is an even number. So the parity flag will be set. What about auxiliary carry flag? During the addition of 5 and 3, we received the result 8. So no carry. So the auxiliary carry will be reset to 0. What about Z flag? Does the accumulator contain all zeros? No, right? So the Z flag will be reset to 0. Coming to sign flag, the most significant bit within the accumulator is 0, so the sign flag will also be reset to 0. So if inside the accumulator initially we have 65H, within the B register we have got the value B2H, and if the carry is initially set to 1, after the execution of the instruction ADCB, within the accumulator we will have the value 18, and in the flags register, only the carry and the parity flags will be set. So we are done with the execution of ADCB. Let's now come to the third instruction, that is SUI 56H. Now what does SUI mean? Subtract immediate. And this is the immediate data that we are sending. So this is the subtrahend. And where is the minuend? It is inside the accumulator register, which is 65. So we are supposed to perform the subtraction 65 minus 56. Now if you remember, I told you earlier that within the 8085 microprocessor, subtraction is not performed. Rather, addition is performed using 16's complement or 2's complement in binary. Since we are dealing in hexadecimal numbers in here, so we will convert 56 to its equivalent 16's complement. So let's do that. But before that, do remember, in the flags register, the carry flag is initially set. Now the immediate data is 56. So 6, that is the least significant digit, we will subtract this from 10, and if we do that, we will have A. Think about it. 10 of hexadecimal is 16 in decimal, and from 16 if we subtract 6, we will have the result as 10. And 10 in case of hexadecimal is A. Now coming to the most significant digit, we are going to subtract it from F, or 15. And from 15, if we subtract 5, we will also obtain 10. And 10 in case of hexadecimal, as I told you earlier, it is A. So with 65H, we will add AAH. Let's now perform the addition. 5 plus A, that is 10, we will obtain 15, which in case of hexadecimal is F. Coming to the next part, 6 plus A, that is 6 plus 10, which is 16 in decimal, and in hexadecimal it is 10, right? Now notice, we performed subtraction in the form of addition. And for cases like this, when the carry is generated, it means the result is a positive value. And the carry is supposed to be ignored, right? And that's why after this particular operation, within the accumulator register, the value 0F will be loaded in binary. Now F in binary is 4 ones. And what about 0? It is 4 zeros, right? So after this operation, within the accumulator register or the A register, the value 0F will be stored. Now I told you earlier, when the subtraction is performed using 2's complement fashion, in that case, if the carry is generated, it signifies that the outcome is a positive value. And thereafter, the carry is to be ignored. On the other hand, if the carry is not generated, that specifies that the generated outcome is a negative value, and in order to perform the subtraction, borrow was taken. Therefore, in case of subtraction, the carry flag is connected to a NOT gate. So the carry, which is 1 in this case, will be fed to the carry flag via this NOT gate. So 1 will be reset to 0. Coming to the P flag, that is parity. For this, as I told you, within the accumulator, we must have even number of ones. How many ones do we have currently? 4 ones, which happens to be an even number. So the parity flag is going to be set. What about AC flag? If you notice, we added 5 with A, and the result was F. So no auxiliary carry, right? So the auxiliary carry flag will also be reset. Coming to Z flag, since the accumulator doesn't contain all zeros, so it will be reset as well. What about the sign flag? Notice the most significant bit within the accumulator register. It is 0. So clearly, the sign flag will also be reset to 0. So if within the accumulator register, at first we have the content 65H, and thereafter if we execute the instruction SUI 56H, by the end of the operation within the accumulator register, the value 0F will be there, and in the flags register, only the parity flag will be set. And this is what we were supposed to find out, right? So we are done with the execution of the instruction SUI 56H. Let's now focus on the fourth instruction, that is SBBM. Now I hope you remember what SBBM does. Subtract with borrow, and what will be subtracted? The content within the memory location, which is pointed by the HL register pair. In the HL register pair, as you can notice, the address F950 is given, and within the memory location F950, we have got the value 38. So from the accumulator's content, that is 65, we are going to subtract 38. Now remember, it is SBBM. So clearly, we have to consider the borrow as well. And borrow is notified by the carry flag. This we already know. And initially, if you see, the carry flag is set. So the operation that we are performing is 65 minus 38 minus 1. We can also add this to 38, right? And if we do that, 38 will be 39 now. Now, as I mentioned earlier, in 8085, we always perform addition. So we need to find out the 16th complement of 39H. So let's do that. Now from 10 we will subtract 9, and from F we will subtract 3. 10 of hexadecimal is 16 in decimal, and from 16 if we subtract 9, the result is going to be 7. And from f, that is 15 of decimal, if we subtract 3, the result is going to be 12, which will be C in case of hexadecimal. So in the least significant digit, we will have 7, because from 10 or 16, we subtracted 9. So we got 7. And from F or 15, we subtracted 3. So we get C. Now we can perform the addition. So 5 plus 7 will give us the result 12, which in hexadecimal is C. Coming to the next part, 6 plus C, which is 12 of decimal, will give us the result as 18. And in case of hexadecimal, 10 is 16, so 11 is 17, therefore 12 is 18. Notice, it generated a carry, so clearly the obtained value is a positive value. So after the entire operation, the least significant 2 digits, that is 2 and C, is going to be loaded within the accumulator register. Now the content of the accumulator, that is 2C, if we convert that in binary, C in binary is 1100 because C is 12 in decimal. So let's have that. Now what about 2? The 4-bit binary equivalent of 2 is 0010. Now do remember, although we performed addition, in reality we were performing subtraction. And in case of subtraction, if the carry is generated, it signifies that the generated outcome is a positive value, and the carry is to be ignored. So this value 1 will be fed to the carry flag via the NOT gate. So the carry flag is going to be reset to 0. What about the parity flag? If you notice, within the accumulator, we have got 3 ones, which is an odd number. So the parity flag will be reset to 0. What about auxiliary carry? In the least significant digits, we added 5 with 7, which resulted in C. So no carry. So the auxiliary carry flag will also be reset. What about Z flag? Within the accumulator, we don't have all zeros, so this will be reset as well. Coming to sign flag, since the most significant bit inside the accumulator is 0, it will be reset to 0. So after the execution of SBBM, within the accumulator, we will have the value 2C. Remember, initially the accumulator had the value 65. And within the flags register, all the flags will be reset to 0. So we are done with our 4th instruction, SBBM. Let's now focus on the last instruction, that is SUBH. So here we are subtracting the contents of H register, which happens to be F9, from the accumulator's content, which is 65. So in the operation, the minuend is 65H and the subtrahend is F9H. Now, like I have mentioned multiple times, in 8085 subtraction doesn't happen, it happens in 2's complement fashion. Since we are using hexadecimal notations, we will use 16's complement fashion. So we need to find out the 16's complement equivalent of F9. And in order to do so, the least significant digit, that is 9, is to be subtracted from 10 of hexadecimal, and the most significant digit, which is F, is to be subtracted from F. So let's perform that. Now from 10, that is 16, if we subtract 9, we will get the result as 7. Now from F, if we subtract F, we will have 0. So the 16's complement of F9 is 07. Now we can go ahead with the addition. Adding 5 with 7, we will obtain the result 12, which in case of hexadecimal is C. Now what about 6 plus 0? Evidently 6, right? Notice one thing, we didn't generate any carry. So this will specify that the borrow was done in order to perform the subtraction. And for that, to the flags register, the 0 will be fed to the carry flag via the NOT gate. So the carry flag will be set. This specifies that in order to perform the subtraction, borrow was needed. Anyway, coming back to our operation, after the subtraction which we have performed in 16's complements way, by obviously performing the addition, the result, that is 6C, is going to be loaded within the accumulator register. Now, in order to find out the status of the remaining flags, we need 6C inside the accumulator in binary. Now, C is 12, which in binary is 1100. Coming to 6, the 4-bit binary equivalent of 6 is 0110. Let's now check out whether the parity flag will be set or reset. Notice, within the accumulator, we have got 1, 2, 3, 4, that is 4 ones. Clearly, an even value, so the parity flag is going to be set. What about the auxiliary carry? We added 5 with 7 and the obtained result was C. So, no carry. So the auxiliary carry will be reset to 0. Does the accumulator contain all zeros? No, right? So the Z flag will be reset. What about the S flag? The accumulator's most significant bit is 0, so the sign flag will be reset as well. Therefore, if within the accumulator register we initially have 65H and within the H register we have got F9H, thereafter, if the microprocessor executes the instruction SUBH, within the accumulator, we will have the result 6C, and in the flags register, the carry flag and the parity flag will be set. Remember, here by setting the carry flag, it is notified to the microprocessor that in order to perform the subtraction, borrow was needed. So with this, we also have completed the execution of the last instruction. It was an interesting session, don't you think? So in this session, we solved 5 problems on arithmetic instructions. Alright people, that will be all for this session. From the next session onwards, we will start learning about the logical group of instructions. So I hope to see you in the next ones. Thank you all for watching.